we have a talk titled RIPE RIS and How to Query the DFZ. The presenter is Thijs de Kock. I would like to introduce him, who will be, Thijs is a software engineer at RIPE NCC and traveled from the Netherlands to join us today. This is Thijs' first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Thijs.
Okay, nice to see you all here, and welcome to my talk. It's exciting to be presenting here at NANOG. And what I will present today is a new way to work with route collector data that we developed over the last year at the RIPE NCC. First is a tool that we needed for our internal debugging, and then we realized this is something that will make working with the data that route collector project like RIPE RIS collects way easier. The main takeaway should be that working with route collector data is challenging in the original format, but that we now are presenting an alternative based on Parquet files that contain all the data in the RIP or the BGP updates from route collector project. And that means that you can use them and query these with SQL or with data science tools and use these workflows instead of working with MRT. So, okay, well, what I just described was the final result. First, I want to take a few steps back to introduce what a route collector project is, how our project works, and how the data is currently used. So, a route collector in a project like RIPE RIS or route views is a BGP speaker that does not have the goal of attracting traffic by announcing routes, but it's just a BGP speaker that captures all the routes that it receives from the peers and collects those in a longitudinal archive. People often talk about the name of the collector, and that's convenient because they all create a file. But for me, that's just an infrastructure artifact of how we design our tools. And I think that our users care about getting the relevant information and are able to process it. And we see that there are significant challenges with the current tools that they use. And the most important thing, and what I forgot when I started here, is that these projects are not a project by themselves, but it's a collaboration between the community that shares data with us and the parties that run these projects. So the RIPE NCC in the case of the routing information system and NCSC in the case of route views. So now I'll dive a little bit into the details of RIPE RIS. We have a worldwide network of route collectors where most of our machines are co-located at internet exchanges, and we pair with the route server and peers that are present locally. But we also have some collectors that have multi-hop BGP sessions, which is a BGP session, but just over the internet. The system is just built out of standard Linux components, so it's a Linux system or VM. It's XBGP as a BGP speaker, Kafka as a message broker, and then there's a lot of custom data processing and plumbing to make things work. If you have a lot of BGP pairs, and I guess for your networks you always have that, but we try to store them, so it's a slightly different problem. You also get a lot of routes and updates. So in the middle of this year, we had around 350 million routes in RIPE RIS for our v4, 78 million for v6, like above 15,000 BGP updates a second that we processed, and 46,000 updates a second, 1 minute average as the peak for that day. And the 1 second peak is much higher because you get a full table, but well, you don't need to process that asynchronously, so that's fine. Then looking at the architecture, I already said there was a lot of processing involved. On this diagram on the left-hand side, so not on the slide, you have the BGP pairs. They have BGP sessions with route collectors, and we cache this data locally, and we push it into Kafka asynchronously. Then from Kafka, we have many processes that consume this data. One very nice one is for RIS Live, where we add a bit of metadata, and then there's a public WebSocket where you can filter the BGP messages that you want to have and consume those from JavaScript, Python, whatever. There is a big data infrastructure that powers our service, RIPE-Stat, which also includes BGP state machine that tracks these routes in an in-memory database for a looking glass over all these pairs. And we have the RIS raw data archives, where we have two main types of deliverables. One are the full table dumps, which we call BViews, that are used by us tracking the BGP state. And we write the BGP updates every 5 minutes. The data is publicly available for download. And what's interesting here is that the raw BGP messages are included, and that our BGP speaker is kind of agnostic to what is in there. The library you use to parse these files then extracts the information and implements the relevant BGP RFCs. So even some illegal BGP messages make it into our archives, such as the, what was it? The OTC, the routes with the OTC attributes of 1024 bytes that were around over the last weeks, and that uncovered some software bugs. We write the RIP every 8 hours, and we write the BGP updates every 5 minutes. We have 23 route collectors. So if you do the math, if you want to consume the data for 1 hour, you need to download 276 files and parse those. So it gets kind of inconvenient, but still manageable. And we see that people use this data in a variety of ways. And now I'll go over this first. And what I want to show off first is an easy way to use it. So I'll show off something in a web application, then I'll show some CLI flow and the script, and then I'll argue that you can do many of these use cases in SQL, and that SQL is actually pretty easy to write. So the first example is from a website from the RIPE NCC called RIPEstat, where we have a bunch of widgets that show internet data. And the one I want to highlight now is called Upstream Visibility, which shows the visibility of one specific prefix over time. To do so, we need to index all this data and make it available to retrieve interactively for the web application. So it's kind of hard on the back end. But in the end, you get a widget where, okay, you can see you have all the pairs did see this prefix at the beginning. Then they made it RPKI invalid, and the visibility drops. And what is interesting here is that you see that the origin stayed the same, the first upstream stayed the same, but it became less visible. And when you go up the BGP path, you see that when the prefix becomes BGP invalid, the distribution of the upstreams changes. So you can see that when somebody makes a typo or intentionally makes something RV invalid, the visibility drops quite significantly, that some of the upstreams filters and others don't, and that an upstream that first was the minority of all the upstreams suddenly is one of the biggest ones. From there, I want to dive from using processed data from a route collector into using the raw data by showing what I see many people do when analyzing this. And as a software engineer, it feels kind of alien to do so, but you can get quite far with downloading a file, opening it with the utility that reads it, BGP reader in this case, and grabbing. And I'm not very good at awk, but I bet you can even get statistics out of the AS path this way. But when as a software engineer, I would want to get statistics out of the AS path, I would write a script. So here I use BGPKit from Mingwei, which also got a call out in the previous presentation before the lunch break. It gives me a list of all the files that are available for this point in time for RIPE-RIS. I parse the files, I iterate over the routes that are in there for a K-root nodes for the VeriSign GTLD Anycast prefix, and I count our upstreams. And I see these statistics. I wait a little bit, like over 10 minutes, and I see these statistics, and I can see how this prefix propagates over the internet and what upstreams they have. And what took a long time in the previous one is not actually downloading the data, it's parsing these files. And for any analysis that you want to do, you need to parse the files again. So every time you do something like this, you wait like close to 20 minutes. So an alternative that we recently documented is to use a database, in this case ClickHouse, to index these files and to do a SQL query on on all the routes that are in there. So here I want to get the first upstream again. So I select the prefix, only the rows that have the specific prefix. I take the AS path and I slice it up and I index it to get the first upstream, and I count how often each of those occurs. This time for the K-root Anycast prefix. And After looking at these use cases, I started to realize that I got a few realizations. First of all, the tools that are easiest to use and that are available online come with a downside because they limit what information you can access. And this is just because it would be hard for them to process the data again for your use case. And then if you take a look at the deep dive and use the MRT files directly, things get complicated. The workflow is complicated, you need to download the files, you need to write scripts, and things become big and slow. And if you look at a lot of academic papers that use this data, they take a very tiny slice of the data that's available for RIS and route views. So these academics that I cite here, they took the data from the collectors named RC00, 01, and 10, instead of capturing using all the data. And by selecting a subset of the data, you lose some routes, you lose some effects, and you introduce a bias. And honestly, myself, I cannot really say what bias is present in all of these collectors, except that I know that in general, full tables that are easily available at internet exchanges are overrepresented. So that's like Hurricane Electric, and that academic networks are overrepresented. The approach of indexing this data in a database is very nice, and I recommend it. But it has its downsides. Like if you use ClickHouse, it's kind of big, not terribly big, but you can append the data at will. If you use Postgres, it's very nice to use. They're very nice operators for more or less specific search, but it gets quite unwieldy. For example, the snapshot of RIPE-RIS for one point in time with all the indexes to quickly look up stuff is 180 gigabytes, and that's kind of big. So if you want to analyze data for multiple days, maybe even a month, or multiple days over a year, yeah, it gets annoying. So from these lessons learned, I want to present our internal prototype, which is graduating into something real, which are Parquet files, which is a data science format that are generated by parsing the MRT data and indexing it and doing a few tricks while creating the files. We have two types of files available, one for the full RIPs, one for the BGP updates. And for now, we'll only keep a short-term archive of these files available for download, just because of disk space reasons and because we want to still be able to iterate on the storage schema. And I want to be really clear that what this allows you to do is not new. You could always download these files, use them, write your script, and use the data. But it just became a lot more accessible to do this because I think that everybody in the room here at least has seen SQL and maybe has written SQL. And it also turns out that, since I wasn't great at SQL myself when I started this, that LLMs are really great at SQL. So you can get a long way with those. Now, I want to give some details of what we actually have available. And what we basically did is that we included the relevant columns from the MRT files, where we made sure that the data that we have there is correct for doing a science-like analysis. And while AS sets are very deprecated, they are present in the default free zone. So that means that when we have an AS path, it needs to be a string. But where we can and where we know that's an AS number, for example, for the peer AS, we will use that instead. There are around there were around 250 million rows for RIPE-RIS in the file they used for this slide. And the files, if you download them, are slightly smaller than the original data if you download it. And that just depends on the compression and basically how the data is sorted. And for BGP updates, the size really depends on how active BGP was. But for typical hour, there are 50 million rows, and it's like around 350 megabytes. So this is a size that you can work with. What we tried to do there was to make files that contain the relevant data, while not adding columns that are not really useful, to have data that covers real-world use cases, and that's kind of ergonomic to use. So while BGP actually is based on BGP messages, and every message can contain multiple prefixes which change, we create a file that has one row for every updated route or withdrawn route, because that's more convenient. And we're really careful with what we edit and what we expose. to end up with files that have a manageable file size that we can make available for download easily, that are easy to process, etc. So after pitching this idea, let's move back to the first example that I showed, which was the first example that I showed on the CLI, which was downloading the file and getting all the announcements for a certain prefix. And in SQL, and this may be my this may be just me after a lot of exposure therapy with SQL. For me, this query in DuckDB is quite readable. I select a few columns, like the prefix, blah, 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 from the file, and I filter for the specific prefix, and I get all these announcements. And when I take a step further, and I express the more complicated example we had before in SQL, you see a similar query. So, okay, we're counting again. I'm taking the second to last element from the AS path for this prefix. So again, the GTLD Anycast prefix, and you see all the upstreams. And when I had this in a script, it took more than 10 minutes to filter the data. But in the query plan at the bottom here, you see that it took 1.6 seconds. And this makes a very big difference, because when you don't know what you're looking for and you're doing what they call exploratory data analysis, you can now test a lot of things very quickly and see if there's signal or not, instead of waiting 20 minutes for everything you want to test. So if you want to look at a certain AS adjacency in the data, or you want to slice it this way, that way, this can become quite interactive. And SQL is a very powerful tool, so I'm showing a very complicated query here, where I honestly needed some LLM help to write it the first time. Because one of the things we do to look at the quality of our route collector project is to look at the number of prefixes we see transiting various tier one networks. And if you think about the previous query we did, this can be quite easily done in SQL. So okay, I select all the rows where this AS is in the AS path, and I just count how many unique rows there are. Now, if you want to do this from multiple networks, and you do this in SQL, you get a join, as you see here on the slide. And if I take it one step further, and I take a file that contains data for both RIS and route views, which unfortunately I couldn't share today yet, I would get a row where it says for each tier 1 AS, for RIS, for route views, for V4, for V6, how many prefixes we see in the data set. And when you really dive deep in SQL, there's a pivot keyword, and you get one big column that basically shows the coverage of RIS and route views in one SQL query, instead of by writing a script. And the big difference is that instead of knowing what you want to analyze before you create the data, you could just have the data set available, and you can write your analysis as you go. What I showed so far were examples using SQL without external analysis tools. But as I mentioned in the beginning, this approach really fits into the Python data ecosystem, where selecting the data is just the first step of your analysis. And if you've done data science, you've probably heard about Parquet already. It's a very common format there. There's a lot of support for it, so it fits into the Python data ecosystem really easily. So I want to show some examples of that. And don't worry here, all the examples that I'll show in the next slides are also available in the GitHub repo that I link at the end. So you can run this yourself if you want to. So again, the first case is simple. I'll just calculate some statistics in a Jupyter notebook. And I count how many rows there are. And there were 1.6 billion BGP updates this day. And then I aggregate over the prefixes. And I get the number of updates per BGP per prefix. And what you see here in this top 5 is that a very steep distribution, with like 12 million updates for the noisiest prefix and like 5 million for the fifth one. But the top 5 doesn't really give me a feeling for how this how the noise is distributed over the complete default-free zone. So let's continue there. So to get a better feeling for what's happening, I use SQL to calculate the cumulative distribution function. So basically, how many prefixes have less updates than every row in this table. And I get a few rows for that. And out of these 20 rows, you see that, okay, like the 7th percentile to the 14th percentile have around 500 updates, and that the median prefix has more than 1250 updates. But still, this is only a small sample, and you may miss a very noisy prefix here. But since you're doing data science anyway, you can plot this. And you see things in this visualization that were hidden in the previous one, where basically now you see that more than 60% of the prefixes have barely any updates compared to the noisiest ones. Then at some point, there's a plateau where prefixes are kind of noisy. And then there's a few ultra-noisy prefixes that really cause a lot of data. And the beautiful thing here is that you can repeat this analysis yourself, and you can edit it. So you can look at certain transit ASNs, various origins, your own prefixes. Or you can split this and have two colors, one for announcements, one for withdrawals. But in practice, most of the updates are re-announcements. Finally, I want to show a real example for one of our data scientists at the RIPE NCC, where this helped us analyzing the cable cuts in the Baltic Sea, which will be presented in the other room after this presentation, where our researchers noticed that a certain AS adjacency showed up in BGP after the cable was cut. So again, it's a very simple query to select all the routes where this adjacency is present in the array of the AS path. Then you bucket it per time window, and you just count. And if you plot that, you see exactly when the internet was routing around the damage and mitigating the cable that was cut in the Black Sea. And the first files for this are available for download now. The process isn't fully automated yet because there was an internal IT freeze, so I'm uploading a few of them from my laptop right now. But the first ones are available, and in a few weeks this will be automated. There's our Python workbooks showing the examples that I just did available in one of my GitHub repos. And I hope that this sparked your curiosity, and that I made a convincing case that route collector data isn't as scary as I thought when I first looked at MRT files. And that especially with these derived files, this is kind of easy to access. So to recap, we introduced a prototype of a Parquet-based format as an alternative for raw MRT files, where we have separate files for RIPs and for BGP updates. The first files are available now. This data is in MRT form is more accessible than you maybe would think, and in Parquet it's definitely accessible, I think. And that with SQL you can do relatively complicated analysis of the complete internet, of your own AS, or specific interest, prefixes or networks you are interested in. And we launched this as a prototype for now, and we really want to hear your feedback about this, to hear whether it's useful for you as general network operators. We know that academics also are interested in this and are using it already. And we want to produce these files for the next 18 months if nobody uses them. But we hope that they're popular, and then we'll continue doing this in the future. And we also want your feedback about which use cases you have, what fields are missing, because there's much more in the raw BGP data that we don't index yet. And because of that, I think that the schema will evolve. So when we add fields, when we remove fields, or something becomes a string instead of a number or the other way around, we will keep producing the old format so you can continue doing your analysis with your scripts for now. And yeah, I hope this made you guys interested in using this data.